So you neglect the interactions between particles, and 2, you neglect the volume subtended by the gas itself. So basically, it doesn't interact with itself, and it doesn't take up any space. Obviously, nothing like this actually exists in real life, but it's a good approximation, and that's how we generally work up in physics. So an ideal gas obeys the aptly named ideal gas law. Physicists suck at coming up with cool names. And what is the, yeah, go ahead, Jacob. Yeah, so basically the particles of the gas, they don't actually take up any space, is what you're saying. So you can keep throwing them into a container and they don't actually take up any space. You've got like this invisible fluid which obeys this equation. And so I'm assuming that looks pretty familiar to everybody, but if it doesn't, so P here, this is pressure. V is volume. Does anybody know what N is in this form? Yep, number of moles and not the animal. R is going to be called the ideal gas constant. We'll just call it a universal constant for now. And T is going to be the temperature, and it is in Kelvin. And we'll see that it's in Kelvin because of the units of this number here, R. So you've probably seen this form in chemistry a lot, I would assume. And so here I'll write what R is specifically. R in SI units is 8.31 joules over moles times Kelvin. So we see here, basically, here's a question. What units does this overall expression have? What units does the left-hand side have? What units does the right-hand side have overall? Anybody? If you look at what the units are for R, you know that N is moles, T is Kelvin. What do we think this is? Yeah, joules. So it's energy. And obviously, if this side is in units of energy, then this side also has to be in units of energy. So basically, another way of thinking of pressure is as an energy density, right? Because you're taking P times the volume and it gives you energy. So pressure is like an energy density, and that's a good way to think about it in astrophysics as well. Yeah. So let's write out what the units are for P in general and SI. P. Remember, the brackets here just means that we're pulling out the units and not paying attention to the actual numerical factor. It's going to have units of Newton per meter squared, which is also the same as joule per meter cubed. And we'll refer to this unit as a Pascal. Okay. And then the units for V, of course, volume in SI is going to be meters cubed. Okay. Now, note a couple of relations here. So typically, if you're on the surface of the Earth, your pressure due to the atmosphere is going to be the aptly named 1 atmosphere, which is 1.013 times 10 to the 5 pascals. And sometimes also used is bar. Bar is related to pascals by a factor of 10 to the 5. Sometimes you'll also see liters used instead of just meters cubed. So you should know that 1 liter, and I'll put the E before the R here, is 0.1 overall meters cubed. Okay, and then the next and last thing that we need to know in this expression is that a mole is just a number, which you've probably seen before. Does anybody know what specific number it is? it looks like this. It's n sub a. It's referred to as Avogadro's number, right? So Avogadro's number is taken to be this number, it's times 10 to the 23, and that is equal to what we call a mole. Keep in mind here that a mole isn't actually a real physical unit, it's just a number. It's a literal unitless number. So it's very different from meters, newtons, joules, anything else that we talk about. Okay. Okay, so you might have seen that expression of the ideal gas law before, but you might have also seen this one. Have people seen both expressions before, or are they? Yeah, okay. So if we know that the ideal gas law can also be written this way, and it can be written as an R and T, well, something we might ask ourselves is how we can relate this factor nr and this factor nk. Well, obviously, if we cancel out t on both sides, then we just have that n times k equals n times r. And here we'll use a little bit of dimensional analysis. So we know that n as, quote, units, though make sure that you don't actually think of moles as a unit, but that's what we'll call it. It's kind of fake. This has units of joules over moles times Kelvin. And so then the expression n times r, it has units of joules per Kelvin, which is the same as the units of n times k. Okay, so if I tell you that n here, this n, is just the number of particles, and I'll use the pound sign to refer to number of particles, then what units does k have to have? What are the units of k? Yes, we can erase that. We've cleared up our confusion. Okay, so yeah, this k right here is actually called Boltzmann's constant. And I'll use the 3 equal sign, or the 3 lines here to denote equivalent to. It's just a definition. It's not an actual equation. That's what we call k. So how could we get the value of k if we know that n is the number of particles? So what is... I mean, we could just look up what k is online if we want to, but if we want to be good physicists, we could use our mathematical skills to figure this out. So we can take n and convert it, use the conversion between moles and the number, Avogadro's number. So n times 6.02 times 10 to the 23 all over 1 mole. So here the moles will cancel out. That'll be equivalent to the number of particles. Now we can write number of moles as big N over NA, Avogadro's number. So then we can write the equation up here above, NR equals NK, as NR over NA equals N times K. So now we see that the N, the number of particles, cancels out, and we're just left with an equation that relates K to the ideal gas constant over Avogadro's number. So we see that K is just R over NA. And if we were to insert the actual values in here, you could then show that this is roughly 1.381 times 10 to the minus 23 joules per Kelvin. Okay, so now we'll do a little practice problem. And I believe this is problem 1.9 in the book, so but I don't think I assigned it for homework. Okay, problem 1.9 basically asks, what is the volume given the following? N equals 1 mole. T is equal to room temp, which is roughly 293 Kelvin. at atmosphere. Okay, so then you solve for what V is. Any ideas what to do here? It's pretty straightforward. We'll just apply the ideal gas law, right? I mean, that's what we're learning about. Obviously, it's probably what we're going to use. So let's go ahead and do it. So we know PV equals nRT. We want to find V. We're given P. We know N. We know R. We know T. Simple enough. You literally just rearrange the equation. T over P. And then inserting all the numbers, we would get something that looks like this. So that's pretty easy and straightforward. If everyone has any questions, feel free to speak up, but this is just a simple application of the ideal gas law. Okay, but now the question is, well, what if we take P and we double it? What happens then? What happens to V? V would go to what? Any ideas? Well, how would we address this problem again? Yeah, exactly. And why is that? It's just because if we look at the ideal gas law, right, and we hold everything else constant, that's something else I should have said here for P goes to 2P, hold everything else constant as well. You see that the relationship between P and V, so if we say PV equals a constant, then you can relate P and V. P is proportional to 1 over V. So if you double this guy, then P has to go to half of itself for this to be satisfied, right? So also, what if we take T and send it to 2 times T? Well, use the same kind of logic. So yeah, so we're going to hold P constant. So V is just roughly proportional to T. So if you take T to go times 2T, then obviously V also has to go to 2 times V. So we'll write our answer there. V goes to 2 times V. Boom. In this kind of idea of like looking at equations, holding lots of things constant, and just looking at proportionalities between 2 variables is always a really useful thing to do. Okay, so always keep that in your toolbox. All right, so now we're going to try to address the issue, or the idea of energy being the thing transferred in getting to thermal equilibrium. So the way we're going to do that is like Schroeder does it in the book. So he says, consider a single particle of gas in a cylinder enclosed by a piston. So let's draw our cylinder. Hopefully make it look okay. Okay, so this is our piston. It's got some handle attached to it. And we've got a single particle in here. It's got some velocity vector v. Okay, and we'll say that the piston area is A. So then the volume is just equal to the length, which we hopefully are also given. Length times A. Okay, so let's assume, make some assumptions. Collisions with the wall are elastic. So as this guy bounces around, as it bounces off the walls, it doesn't actually lose any momentum in that collision, okay? So we assume collision is elastic. Basically the most idealized case that we could possibly have. And we're also going to assume that these surfaces here, the wall surfaces, are completely smooth, so that as I drew right here, this is basically reflecting like a ray of light would off of a mirror or something like that. So it's just going to basically be that this angle here is equal to that angle there, even though they don't look like they are because I'm poor at drawing things. Okay, so assume elastic and smooth walls. So how does temperature relate to energy? Well, we know that PV equals nKT describes what we call an ideal gas. So consider the pressure on this piston, for example. What is it? Well, pressure, we know it has units of newtons per meter squared. So that is a force divided by an area. So, well, when does this piston actually feel a force? It's only going to be when the particle actually hits it and bounces off it, and it feels an instantaneous force due to the momentum of this particle changing from that way to the other way, right? So what does it feel when this happens? So what? Whoa. Okay, so what force does it feel when the particle bounces off of it? Well, we know that piston force is going to be equal and opposite to the force that the particle feels. And we know by Newton's law that F is just ma. And we can also be sloppy and say that this A right here, we can just write it as delta V over delta T, where this delta T is kind of confusing because, well, the change in velocity is instantaneous here, but let's just roll with it. And in this case, we are only considering the collisions off of this piston right here. And if we take our coordinate system to be like this, so that this is y and this is x, well, then we only actually care about the x velocity here, right? Because it's the only one that's changing. Delta Vx over delta t. All right. So now we can write the pressure that the piston feels. It's just going to be the force on the piston divided by the area of the piston. And so we've got all of that, so it's just going to be minus m over a, which stands for area, times delta Vx over delta t. Okay, so we've gotten that far. Oh, go to the next page. Okay, so yeah, as I was saying before, like this expression right here is going to tell us what the instantaneous force is, only when this particle actually bounces off of the piston, right? But what we actually want is we want to talk about the pressure. Well, the pressure is going to be a more macroscopic quantity, which is hopefully going to be something that we can measure all the time and find some kind of average value. So what we actually want to determine is the average value of the pressure here, because what we've just written is an instantaneous pressure. So we'll put a bar over it now to denote that we want an average. And that'll be pretty common in general. You just put a bar over something when you want to talk about it being averaged. So let's just take that expression and slap a bar over it. That's an x, delta t, and then the average of that. So what we really want to do is we want to take the instantaneous pressure and we want to average it over the time it would take for one cycle to complete. And basically what I mean by that is for the particle to hit, go down, and then come back. So then we could always just divide it by the number of cycles that occur. Yeah, the meeting is being recorded, George, just so you're aware. I've tried to pay attention to the chat as much as I can. Okay. So what we want to calculate now is basically the time that it takes for one cycle to occur. So let's average over one cycle. And by cycle, whoa, can't spell today. What I mean by that is just down and back. All right, does anybody have any ideas what this time will be? How long it'll take to do this? So we'll refer to this quantity as delta t. Well, we know that the cylinder suddenly grew. So this length is L, right? So how long, if it has an x velocity of Vx, how long does it take for it to start here, go down, and then come back? Any thoughts? 2L Yes, exactly. So the time it would take for it to go down once would just be L over V, and then to come back, 2L over V. Yep, 2L over V. And specifically here, since we only care about the x direction, it's going to be Vx, because it's only going in that direction. Okay, so we've got delta t. Now we just need to figure out what delta Vx is, right? Well, that's also going to be pretty easy. So let's envision our initial situation, basically. So right before it hits, its Vx looks like this. And then after it hits, its velocity looks like this, right? So what is delta Vx? Well, you got to first take this magnitude, collapse it down to 0. So that's 1 Vx. And then you've got to turn it the opposite direction. So that's 2Vx. So Vx plus Vx, 2Vx. And it's actually negative. Be careful there. All right, so now let's put all this together. So P bar piston equals minus M over A times minus 2. Why is it negative? It's negative because it's flipping directions, basically. So you have to subtract Vx. So the change in Vx for it to go from positive Vx to 0 is negative Vx, right? And then for it to go further negative, it's got to add another negative Vx. Does that make sense? Hopefully. So if we insert this expression up here, 2Vx over 2L over Vx. So we're just taking this expression right here, plugging it in for delta Vx up here, and this expression for delta t and plug it in right there in this expression. We can, why can't we just consider minus Vx goes to plus Vx? Yeah, that would be the same thing. Yeah. So if you were going from minus Vx to plus Vx, the change would still be 2Vx, right? Because you would have to add 2Vx to the negative Vx in order to get to plus Vx. Oh, but I see what you're saying. Oh, so you're saying start with minus Vx. Well, the reason we want to start with plus Vx is because we're considering the reflection off of only this surface right here, only the piston. And so we're saying that the piston is at like the positive x direction down here. If you wanted to consider starting with minus Vx, that would be talking about the reflection down here, right? So we're only considering the reflection off of this surface right now. You could do it the other way, for sure. So if we take this and we simplify it, we will get M over, yeah, not a problem, A times L. And that'll be all times Vx squared. So you see the 2's here, they cancel out. And then we've already said that volume is just area times length, obviously. So this is mVx squared over V. That is what we're going to call the average pressure that the piston feels. And we'll box that. Okay, so Schroeder gives some good prompts. So he basically says, like, in words, why would you expect that there are two factors of Vx here? Why is it Vx squared? Kind of turn on your physics intuition brain and try to figure out why you might expect this if you were a theorist or something and you were just considering the ideal gas and you were just considering this for the first time. Well, so basically in words, why should P bar be proportional to V squared? Well, basically because you have this expression here. You know it's going to be proportional to delta Vx over delta T. You know that delta T, you pick up a factor of 1 over V. And for delta V, you pick up a factor of V. So obviously you should expect in general that P bar is going to go something like delta V over delta T. And if you also consider these scaling relations between delta t and v and delta v and v, then you would expect this goes like v squared. Okay. So now let's go to the next page. So how do we extend this to n particles? So we've only considered one particle so far. Well, the same exact derivation will go through, except now we'll talk about p bar, and here implicitly what we have is p bar piston, but I'll stop writing the piston for the moment, okay? But just know that that's what that is. So we'll get the same thing every single time. So every single particle will have an x velocity. We'll take it, we'll add it, take it, we'll add it, and here we'll only consider that they're all the same particles, so they all have the same mass. And we'll add up n of them, v times nx squared, and then average it over n. Give us the average. Or sorry. No, that's right. Oh, sorry. No, it's over v. Because our expression previously was this, mvx squared, and that's just divided by the volume every single time. So that's why you only have this factor of v under the numerator. All right, so now in practice, for n much greater than order 1, we will just neglect the bar. Since the function approximately becomes continuous as you add up more and more of these particles. You don't get such a discrete counting between all these particles colliding with the piston and bouncing off. As you put in more and more of them, it starts to look like this is a continuous function. So we just generally refer to it as the pressure rather than the average pressure because they approach the same thing. Since p bar is roughly continuous. So we will neglect to write the bar. All right, now, another way to write the right-hand side. And to denote right-hand side, I'll just literally write RHS for right-hand side. So we have n m vx squared bar is going to be another way to write this, basically. So the reason that this is so is since vx squared bar is literally defined as vx1 squared plus vx2 squared dot vnx squared all over n. That's just the definition of an average. Then we can write p times v equals n m vx squared bar. And this will just be the same thing as what we have up here. So all we've done is we've dropped the bar on the p, first of all, because it's approaching continuity. We've multiplied by the volume in order to get to the other side, the left-hand side. And then we've used this definition for what an average is of this squared velocity and just inserted the definition here. And so do note that this quantity right here, the average of the square velocity, it is not the same thing as the average squared. So yeah, vx squared bar is not equal to vx bar squared. So don't ever confuse those two things. So now all we have to do is summon the ideal gas law. And to avoid writing it over and over, I'll just call it the IGL. So that is PV equals NKT. So now we have that we can write NKT equals NMVX squared average. Yeah, go ahead, Carter. Mm-hmm. Where are you saying that? Sorry. De Wish I could have you point at something. You talking about this right here? So right here. Yep. Mm-hmm. Correct. Yep. This term, the Vx. Yeah. So this is correct. Yeah. So this is a squared here. So basically, you're taking all the Vx squareds, you're adding them all up, and then you're just dividing by how many there are. So you're literally taking the average of the quantity Vx squared. So that's why this side, it's already squared, but it's the average of that quantity. Does that make sense? So like if you want to consider the average of like just some quantity x squared in general, or if you want to consider the average of x in general, what you would do is you add up x1 plus x2 dot 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 xn, and then you just divide by the number of those things, right? So that doesn't change if now you're considering x squared, some average, or x cubed. If it's x cubed, now you just add up x1 cubed plus x2 cubed dot 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 xn cubed over n. Does that make sense? That's just how you define the average. Yep. Yeah, totally legal. Yeah. Zakai, what's up? Mm-hmm. It is a definition. Yeah, there are three bars here. Yeah, anytime I put the 3 bars, you have to trust whatever I say because I'm literally just defining it that way. Okay. But this is a well-defined quantity, just so we're all aware. Okay, so what were we doing just now? Well, we said we're going to summon the ideal gas law, which is PV equals nKT. And we've also figured out that we can write PV in terms of the velocity squared averaged, right? So what we're going to do is equate this PV to this PV, which says that we can equate this right-hand side to this right-hand side. So if we do that below, what we can do is we can cancel out the n's because they appear on both sides. We can get kt equals mvx squared bar. Or we could equivalently write this in a way that looks potentially a little bit more familiar to us because we're familiar with 1/2 mv squared being the kinetic energy of some system or particle. Mvx squared bar. And so now we've found some way to relate the temperature to what we would generally think of as like an average translational energy. So think of this as average translational energy. Okay. Now, that was only considering the x bounces. So we only looked at when it was only being considered to bounce off the x surface of that piston. So if we realize that there are 3 directions, right? There's x, y, and there's z. So in reality, we have x, we have y, we have z, we also have time, but it's not bouncing off any time direction here. We're not going to get into anything too crazy like that. But so if we consider each of these directions separately, we would get the same result that we just did. And so what ends up happening is that we would find that we have 1/2 mvx bar squared being equal to 1/2 mvy bar squared equal to mvz bar squared equal to 1/2 kt. They all contribute the same 1/2 kt. Well, if we throw the 1/2 on it. So basically then we can write our average translational kinetic energy if we're working in 3 dimensions. That's just the sum of these 3 terms right here. So we're going to write average translational kinetic energy as this k bar trans equals 1/2 m v bar squared, and this v is all of the v's. So you're basically just taking a dot product here of the three directions. So we've got 1/2 m times vx squared plus vy squared plus vz squared. So what should we have on the right-hand side here? So we know that each one of these, I'm sorry, these should all have bars over them. And the bar is distributive, so just distribute to the v's, the y's, and the z's. So what should we have on this side? Anybody? Yep. 3 halves kt. Cool. That is a pretty fundamental result. So we see that basically what this numerical factor, which we call the Boltzmann constant, is doing, roughly, modulo a factor out here in front, is it's converting between temperature and energy. So K converts, or we won't say converts, we'll say relates temperature and energy. I'll just write it out. Well, let's be careful with that. Translational kinetic energy, because there might be some potential energy in like chemical bonds or something, which is not necessarily related to temperature. That has to do with phase transitions. Yeah. So something to keep in mind, just a little numerical fact. If we consider T to be room temperature, which is roughly 300 Kelvin, this is generally what we'll mean when we say room temperature, although who knows if there's actually any room out there at this temperature at any specific point in time. Then K times T is roughly 4 times 10 to the minus 21 joules. Now, if we're doing our physics at room temperature for the most part of our lives, this is kind of an ugly number to work with. It's obscenely small. So what a lot of people do is they define a different unit of energy called the electron volt. So 1 eV, it's called an electron volt. And basically it's just the amount of kinetic energy that an electron would have if it's accelerated through a 1 volt potential. And how much it has, if you calculate it out, is 1.6 roughly times 10 to the minus 19 joules. It's like 1.609 or something like that, but whatever, close enough. So in that case, if you use electron volts, KT ends up being roughly 1/40 electron volts for room temperature. So that's not a bad number to just have in your pocket, just in any case somebody asks you something to do with thermal physics at room temperature, you automatically know that you can calculate it in EV if you just divide by 40. Okay, and I guess we are technically out of time. I will likely, since we've expired this hour and not gotten through the amount of stuff I wanted to do, I'll probably record a bit of a lecture in order to cover basically the partition theorem, and probably get through heat and work, and potentially cover up through compression work. And then we'll hopefully finish the chapter on Friday. So pay attention to me posting some videos onto Blackboard. I'll probably record that like later today or something. Does anybody have any questions about what we went through today, how this derivation goes through? All of this lecture will be uploaded as well to Blackboard. Was anybody able to see the stuff that I posted the other day? Did that get posted just fine? Yeah? Okay, cool. All right. So was this clear? Was this helpful at all? Or was it just kind of confusing, too fast? Let me know if I'm going too fast, if I'm going too slow. Like, I need feedback here. So if you have any, feel free to shout it. Anybody? Nope. No feedback? Okay. That's fine too. Here, let me get rid of that. So yeah. So yeah, we are, I'll post videos, and I guess office hours will start right after this ends, and I'll just be in my personal meeting room on Zoom. So if you want to join that, feel free to. And make sure you're working on the homework. I know we haven't really covered a lot of the content in class so far, so that's why I'll post a video so you can get started on that and make sure you're not saving it all until Friday. Okay? So just pop into office hours if you have any questions. Otherwise, we'll meet again on Friday and I'll post lectures online. All right. Thanks all for coming. Hope you have a good rest of your day. All right.
Thank you, Professor.
Yeah.
Thank you.
See you.
Thank you.
Thank you.